Okay, hello everyone. We are on the second part of this video recording. Still, we are on the lesson binary operations. So in this video, we will be classifying binary operations by their properties. Okay, so the first two properties are presented here. Okay, and let me read. A binary operation star on set A is associative if for all A, B, and C in set A, okay, the operation A star B and then star C will yield the same result when we perform the operation on B and C first, and then with A. Okay. Say for example, if set A is the set of real numbers, and we consider star to be the ordinary multiplication and ordinary division, then it is associative because associative property holds on the set of real number. Then, so under multiplication and under division, associative property holds for the set of real numbers and all of this its subsets, okay, such as the set of integers, the set of and its subsets. It's not all, but some of the subsets, the set of integers, the set of rational numbers. Okay, so this property holds. Then a binary operation star on set A is commutative if for all A, B in A star B is equal to B star A. Okay, so if, for instance, if you consider the ordinary addition on real numbers, then that a commutative property holds because A plus B is equal to B plus A. The same is true when we consider star or when we define star to be the ordinary multiplication in the set of real numbers, commutative property holds. Okay, A star B is equal to B star A. Okay, next, we define a binary algebraic structure, okay, or a mathematical system or algebraic system to be a non-empty set S together with one or more binary operations on S. So we can denote this using this notation. Okay, we consider S and this binary operation star, or kasi the definition says together with one or more binary operations. So it could be more than one binary operation. So we have this set S, the first binary operation, and the second binary operation, and so on. Okay, so that's algebraic structure. For example, when we consider the set of real numbers, say that's R, and the binary operation star, say such that star is the ordinary multiplication. So that is an algebraic structure. Okay, let's consider this definition. Let an algebraic structure, a binary algebraic structure, okay, let this be a binary algebraic structure. An element E of S is an identity element for star if A star E is equal to E star A, which is also equal to A. For all A in S, for any element in S, then that element, okay, star, the identity element is always equal to the element A. Okay, say for example, in the set of real numbers, under ordinary addition, the identity element is 0, such that any real number added to 0 is the real number itself. And then under the ordinary multiplication, the identity element is 1. Okay, such that any real number times 1 is equal to the real number itself, and 1 times any real number is the real number itself. Okay, next. So I'll be giving examples in the next slides. Okay, let's consider this definition. Okay, so this is the identity element. This is if star is a binary operation on A, and an element E in A is the identity element of A with respect to star, if, okay, for all A in A star E is equal to E star A, which is equal to A. Okay, this is an alternative definition. Okay, let's consider these examples. So 1 is an identity element for the set of integers, the set of rational numbers, the set and the real numbers with respect to multiplication. Then 0 is an identity element for the set of integers, the set of rational numbers, the set of real numbers with respect to addition. Okay, I've mentioned that earlier. Next, let's consider okay, this definition. Okay, let star be a binary operation on A with identity element E, and let A be an element of set A. We say that A is invertible with respect to star if there exists B in A, such that A star B is equal to B star A, which is equal to its identity element. So for us to identify whether a given set is invertible or not, first we have to make sure that it has the identity element. So if it exists, we say that B is an inverse of A with respect to star. And we write B is equal to A inverse, the inverse of A. But we have to take note that inverses may or may not exist. So if it exists, then we can find it. Say, for example, so I have here a set of examples. So example 5, every x in Z, so or every integer has inverse with respect to addition, because for any integer x, then x plus its negative is equal to negative x plus x, which is equal to 0, the identity element of the integers, the identity element under addition. However, very few elements in Z have multiplicative inverses. Okay, there are numbers, say for example, very few elements in Z have multiplicative inverses, say 1. And the inverse of 1 is 1. But the inverse of 2 is 1/2, which is not an integer. Okay, next example. So let's start the in binary operation on Z defined by, for all A, B, and Z, A star B is equal to A plus 3B minus 1. Okay, first we have to prove that the operation is binary. Okay, we can show that the operation is binary if it is closed or closure property holds. So take note that this is taken with respect to the set of integers. Okay, so we will let A and B to be integers. Then A star B, okay, as defined in here, this is A plus 3B minus 1. So we have to take note that B is an integer, so 3 times B is also an integer. Then this is -1 or -1. These are integers. And we are sure that the sum of integers are integers. So therefore, it's closed. Okay? Closure property holds. So we will say that star is a binary operation. On the set of integers. Next. Determine whether the operation is associative and or commutative. Okay, let's see. How do we define A star B? A plus 3B minus 1. So, again, we will let A and B to be integers. Then, A star B is equal to A. Okay, let me double check it. A plus 3B minus 1 plus 3B minus 1. Okay, A plus 3B minus 1. Okay, then how about B star A? Okay, so paano natin define itong operation na to? We have the first member plus 3 times the second member minus 1. So B star A is equal to B plus 3A minus 1. Then A plus 3B minus 1 is not equal to, okay, this shows that A, note that, okay, note that A star B is not equal to B star A. So this implies that commutative. So it's not commutative, or commutative property does not hold. It's not commutative. Okay, on the set of integers. It's close. The sum or the result is an integer, but it's not commutative. How about associative? Okay, for associativity, we need to get 3 members. So we will let A, B, and C to be the set of integers. Then, okay, we have A star B star C equals. So again, let's review how do we define A star B? We take the first term plus 3 times the second term minus 1. Okay, so this time, this is the first term, this is the second term. Or we take the operation like this one, we can do it this way. So we consider this is the first term and this is the second term. So we have the first term A star B plus 3 times the second term minus 1. Next, we can expand this further. So we perform star in A star B. So how do we do that? We take the first term plus 3 times the second term minus 1. Okay? And then copy the remaining terms plus 3c minus 1. So this is equal to A plus 3b minus 1 plus 3c minus 1. So this is A plus 3b plus 3c minus 2. A plus 3b plus 3c minus 2. Okay, how about if we have A star and then B star C. So this is our first term and this is our second term or second member. So by definition, we take the first member plus 3 times the second member, B star C, and then minus 1. So this is equal to A plus 3 times, let us perform the operation here using the definition of star. Okay, by definition, we take the first term plus 3 times the second term minus 1. And then that's minus 1. So this is equal to A. Then let's distribute B plus 3B plus 9C minus 3 minus 1. So this is equal to A plus 3B plus 9C minus 4. So since A star B star C is not equal to A star B star C, then associative property does not hold. So this means that the operation is not commutative and at the same time it's not associative. Okay? And it happens. It's not always the case that a given binary operation is commutative and a given binary operation is associative. Oops. Okay, let's consider the third one. Determine whether the operation has identities. Okay, let's try to find out. Meron kayang identity ito? Okay, such that A plus the identity of, let me rewrite that. A star the identity. A star the identity, which is equal to the identity star A, which is equal to A. A star identity. Okay? If we apply the operation, this is A plus 3E minus 1. Okay? Again, let me check. A plus 3B minus 1. So A plus 3E minus 1. Okay? If it has an identity, the sum should be equal to E. To 1, I'm sorry. To A, I'm sorry. This is equal to A. So let us try to consider this. So A plus 3E minus 1 is equal to A. So this implies that 3e, a plus 3e minus 1 is equal to a. If we subtract a to both sides of the equation, this implies that 3e minus 1 is equal to 0, which implies that 3e is equal to 1, which further implies that e is equal to 1 over 3. Okay. But then another thing that at this point we're saying there is an identity element, and the identity element is 1/3. But we need to verify, because by definition, A star E should be equal to E star A, which is equal to 1. Okay. What if we have E star A? E star A, this is E plus 3A minus 1. Okay, and this should be equal to A if E is the identity element. So this implies that E plus 3A minus 1 is equal to A, which further implies that E is equal to 1 minus 2A. Okay, so we have two claims here. So E is equal to 1/3, which is equal to 1 minus 2A. Okay. So this says that E is 1 minus 2A. E is equal to 1/3. So seemingly, this could only be true if we have a specific value of A. Okay, this is actually not true. These two are not equal. So this implies that there is no identity element. Which is actually not bad, because it's not always the case that there is an identity element. And definitely, there is no inverse. If we cannot identify an identity element, then definitely we cannot identify an inverse. Why? Because when we say a number has an inverse, a number A has an inverse, A inverse, okay, A time star A inverse. Okay, if A inverse exists, then A star A inverse is the identity element. And take note that there's no identity element, so there's no way that we can identify an inverse. Okay, and let's try another one. Okay, let's have the next example. Let star be a binary operation on the power set A. Okay, we know that the power set of A contains every subset of A. Okay, defined by, for all x and y, these are sets, no? For all x and y in the power set of x, x star y is equal to x intersection y. Okay, we have to prove that this operation is binary. Okay. So we will let x and y to be in the power set of A. Okay, then x star y, x star y, x star y, okay, is equal to x intersection y. Okay. Then what is x intersection y? X intersection y contains the elements that are both in x and y. If x is in x intersection y, then x is in x and x is in y. That's how we define the intersection, right? If the intersection is empty, there's no intersection, or x and y has no common element, then if x intersection y is an empty set, okay, then an empty set is a subset of the power set of A. So which implies that x intersection y is in the power set of A. If x intersection y is not an empty set, okay, not empty, then x intersection y is a subset of x, and at the same time, x intersection y is a subset of y. But we have to take note that x is a subset of the power set of A. X is actually in the power set of A. Okay? So, x is a subset, x intersection y is a subset of x. And the power set of A contains all of the subsets of A. Okay, so x intersection y is an element of the power set of A. That is a subset. Okay, or x intersection y is a subset of x, which implies, and note that x is a subset of A. This implies that x intersection y is a subset of A, knowing that x is a subset of A. Kasi nasa power set nga siya, which implies that x intersection y is in the power set of A. Okay, so this means that the operation is binary. Therefore, star is binary, a binary operation. Next, determine whether the operation is associative or commutative. Okay, let x, y, and z to be in the power set, okay, of A. To be in the power set of A. The power set of A. Power set of A. Then, okay, for associative, A, x, star, y, star, z equals. So we have x intersection of y star z. Okay, this is how we define star, no? Then let's define star in y and z. So this is x intersection y intersection z. Then the intersection of sets is associative. So we can say that this is equal to X intersection Y intersection Z. And this is equal to X intersection Y. This is X star Y. Then intersection Z. So X star Y. And then this is intersection Z. Then we can write this as X. Okay, intersection star Y and then star Z. So this implies that it is associative. Okay, associativity holds. Okay, then consider commutative. Let's try to observe if commutative property holds. Then X star Y is equal to X intersection Y. Okay, which is equal to Y intersection X. Okay, diba? If X is in X intersection Y, then X is in X and X is in Y. Okay, and X is in Y or X is in X, which implies that X is in Y intersection X. Okay, which is equal to Y star X, which implies that commutativity holds. Okay, then 2 down. Next, determine whether the operation has identity element. Okay, let's see. If there is an identity element, so we will let X and I think a null set to be elements of the power set of A. Oh, the intersection. What should we intersect with X? Oh, it's not a null set. I think the identity element is X itself. Let X be in the power set of A. Then X star X is equal to X intersection X. And the intersection of X and X is equal to X itself. Okay. So I'm trying to say now that X itself is the identity element. Okay. So which implies that for all X in the power set of A, then X is the identity element. O, siya pa rin yung identity element. Kasi ano yung i-step na pag kinuha natin ng intersection to that set. But the identity element should be unique and X is not unique. Oh. Oo nga. So, X is not the identity element, but yung set na pwede lang na, teka, ano ang pwede nating i-intersect sa isang set X para ang intersection ay the same set? definitely, ang answer natin should be the same, set X. However, if we have the identity element should be unique, there's only one identity element na sa lahat ng set, yun dapat. But if we consider so xy in the power set of A. So if we consider x to be the identity element, then x star y is equal to x intersection y. Okay. X intersection y, which is not always y. X intersection y is not always y. So we cannot claim that x is the identity element. Nasad ako ng slide doon. So which implies that there is no identity element. Okay, kasi kung meron tayong identity element, identify natin ano yung set na yon. Okay, na pag pinerform natin yung binary operation, ang sagot should be the same set. Kung yun sana, that is the empty set eh. Pero ang operation natin ay intersection. So there's no identity element, which implies na wala rin namang inverse. So for this example, okay, nakalagay dito example, but I will consider this as an exercise. Okay, because the star is defined to be the addition, the operation star is defined to be addition of two 2x2 matrices, any 2x2 matrices, and I think you can answer this. And this is the part of your activity. I consider this an assignment. Okay. Example 8. And do I have example 9? Okay, this is proving, and I think I will give the proof to this on to our next video. Okay, I'll stop the recording.